Alrighty, folks. Picking up where we left off the other day. I think we got as far as talking about clastic sedimentary rocks, how they form. I gave you a couple examples of what they were, which left organic and chemical. We did not talk about organic, right? Okay. So, much like clastic sed rocks, organic sedimentary rocks are made of bits and pieces of stuff that's lying around at the surface. Okay. The big difference here is that a good percentage, and no, we don't have really a number for this, but a good percentage of the clasts, again, the fragments, pieces, parts, are organic in origin. That's the main difference. You're still going to get, bits of sediment, inorganic sediment in there, silts and clays and sands and whatever. Think muds. But a big chunk of it comes from organic material, be it seashells or decaying plant matter. That's our big thing. Plants are organisms too, right? Always forget that. Lithification is fairly straightforward, and I shouldn't really say no cementation necessary. You're still going to have groundwater flowing through this stuff. It has, materials dissolved into it, and sure, it's going to leave a slimy sludge, slimy residue behind. But in all honesty, when you think about decaying organic material, it has pardon the word, sort of a stickiness unto itself already, right? And when that's allowed to dry out, it acts as a cement as well. And in fact, let me sort of try and reword that here. Cementation, I don't know what, not always necessary. But you guys, what's a great example of an organic sedimentary rock? We talked about it a little ways back, so some of you might know this already, regardless though. Yeah, coal's the one that should immediately pop to mind for you guys. And coal, when you see a vein of coal, which you don't really anymore, because we mine the bejesus out of everything, but picture driving down the road and seeing your average outcrop on the highway, a rock face, cliff, you might even call it, and a big dark band, okay, going through it. And that big dark band turns out, as you get closer, to be coal. Well, that band of coal represents an old swamp or an old marsh. All right, and while not everyone has gone up to or attempted to step into a marsh or a swamp, I think we could all kind of conjure an image of how mucky and muddy and whatever-y it is, okay? So yeah, there's all that vegetation, and I'm sure a handful of critters, but there's also that muck and mud, usually, as I said, silts and clays and whatnot. Coal has an extra something going on. I always use the word distilling. Very soon you guys will have coal in your hand in geology and earth science. We don't get a hunk into your hand, but you've come across it in life here and there. And it never feels quite right. It always feels a little too light, almost plasticky, a handful of different things that just really set it apart from other rocks. And briefly, a few years back, they were talking about clean coal and so on and so forth. If you've ever stirred up the bottom of a fish tank, again, this is a select audience, but a handful of you might understand this. There's some funk that comes up. It usually bubbles up as you're stirring, right? And you might get a sulfury smell or something even worse. That stuff is in the coal as well. But something happens in the processing of coal. And one of these days I'm going to take a sabbatical and study coal. I never thought I'd say something like that. But it's intrigued me always because it's distilled, steamed. It's not steamed out, but again, it gives the same sort of impression. You're supposedly down to just mostly carbon at that point, okay, with coal. And how it gets from that mucky, muddy swamp down just to the carbon, that's the missing gap, even for me. So I'd love to take some time and study that one of these days. You're going to see two coals, actually. You'll see one in metamorphic rocks called anthracite, and it's processed even more. It'll come close to looking like the obsidian rock. But there's others, okay? Another rock you'll see is coquina. Coquina, you guys usually call granola bar rock or Rice Krispie rock. It's made up of seashells and sand. It's a hunk of beach, and for that reason, it's one of my favorites. I love the beach. So it's the stuff that breaks down to eventually make sand. All right. I think we talked about that the other day when we asked everyone what glass was made of, and a lot of you said sand, and I'm like, well, sand is a lot of things. We need pure quartz crystal, sand. But good old-fashioned beach sand is mainly seashells, just broken down into pieces. All right, so not a whole lot on organics, okay? They're very similar to clastic, just we have a big component of it being organic in origin. Questions about organic sedimentary rocks and or their lithification and or examples therein. Okay. Again, that theme that's going on where I told you basalts, and you're all supposed to smile and nod at me. Well, the same thing's going to go with sedimentary rocks, okay? I'm never going to hold a hunk of something up in here, but I'm going to say sandstone or shale, or you want to know. So, make that connection, be it in lab or just out in the world. These are rocks that you guys are more familiar with than anything, really. I always joke it's sort of our collective unconscious from our caveman past or something like that. But you guys are always way more comfortable with the sed rocks, even though you're going to end up with like 15 of them, I think. You don't really get fazed by them anywhere near as much as the igneous. So for some reason, we're more comfortable with them. Okay, so the hard ones, end quote. It's not really hard, but again, we use some words that make a handful of folks uncomfortable because they're chemistry words. Ew. All right, but they're not bad, and they're actually kind of cool. The idea that you can grow rocks in water, right? So right off the bat, I hit you with two big words. Deposited isn't the big word. Deposited by precipitation of minerals from solution. So hopefully deposit. You've all made a deposit at the bank, for example. All right, that just means to put down. Precipitation and from solution. That's where people tend to get a little antsy. So precipitate doesn't mean rain or snow or sleet in this case. All right.
Not necessarily, but similar. Just in process.
We'll see when we get through the definition if you still feel that way or not. You let me know. All right. So we're not talking about rain or sleet or snow. What we mean by precipitation is basically coming out of solution. Now, in order to understand what coming out of solution means, we need to talk about what going into solution means. All right? And this one you know. This one you do, I don't want to say every day, but almost every day. Putting something into solution is dissolving something. All right? So now there's some arguments about when you're making hot cocoa or Nesquik. Are you really truly dissolving it, or is it just staying in suspension? Okay, there's some arguments to be made there. But you know what I mean. You've got a cube of bouillon and you're making broth. You've got, like I just said, you're making some Swiss Miss. You're doing this. You're making Kool-Aid, okay? You're dissolving something into water. Once something is dissolved into water, it is what we call a solution, okay? So the trick is to get it back out of solution. How do you undissolve it? So precipitating is undissolving. All right? And we're going to take some time explaining how, there's a couple ways, how you can undissolve stuff. Two examples we're going to be aiming towards. Rock salt, halite, whatever you want to call it. Okay, in sedimentary world, it's rock salt. In minerals, it's a halite. And then limestone. Are there other chemical sedimentary rocks? Sure. We're going to talk about a couple? Yeah, probably. But these are the two big ones. These are the example ones. So a lot of this is going to be what I more or less just said to you, but just printed out. So sediments crystallize. I didn't say that today, but we did mention it during the rock cycle. They grow. Little crystals grow. If you made rock candy with your grandma or something sometime. I've actually never made rock candy, but it's so ubiquitous, the example. So the sediments crystallize. Minerals come out of, precipitate, come out of solution. These minerals were previously dissolved in water. So this is, again, just summarizing what we just said. These PowerPoints are now up on Blackboard for you as well. And the next couple ones, too. While I was putting this one up, I put the next couple up. Okay, another word. Saturation. You probably know this one. But to be saturated is to be full of something. 100% full. You are saturated. If you were to get a really far out parking space, it's raining like crazy, and you do your best, you run, hop and skip to the building, and you get in here and you might say, oh my gosh, I am absolutely saturated. You probably wouldn't say that. You'd swear and say you're soaked. But it's the same idea, right? You cannot hold any more water on you or about you. In fact, you are so full of water that you are leaving a puddle on the floor, okay? You're absolutely, positively saturated. Well, in the world of solutions, going back to Swiss Miss, my usual go-to, all right? There are instructions on the box, right? Yeah, sure, you usually cheat and you buy the packets. But depending on who's doing the shopping that week, they might just come home with that big old canister. And you got to do spoons. And even with the packets, it never comes out right. Because if you look at it, they're for 8 ounces of water, typically. Not one of those mugs in your house is 8 ounces. They're 10, 12, 16. Some of these tankards people carry around. Even worse. The point is think about it. If Swiss Miss could have you dissolve a quarter cup of Swiss Miss into 8 ounces of water, don't you think they would? Because it'd sell more Swiss Miss, right? Hell, put a cup in. It'll be great. No, as it turns out, only, I'm making up a number here, 3 tablespoons of Swiss Miss can you dissolve into 8 ounces of water. It's just all that water will hold. Same thing is true. Let's say you went to the doctor and you have a sore throat and they say, go home and gargle with salt water. Well, I don't have any salt water. Okay, put 2 tablespoons of water and 8 ounces of salt and 8 ounces of water. There's only so much of any substance that you can dissolve into a certain amount of water. All right? That makes it saturated. Okay? And it's different for everything. Talk about limestone a couple minutes ago, then we're dissolving calcite into it. Talk about the rock salt. We want to make rock salt. Well, then only so much halite or rock salt you could dissolve into water. back to Swiss Miss as well. Kool-Aid, anything else you've tried to make. You guys still make Tang? I don't think people make Tang anymore. That's when I was a kid. But again, there's only so many scoops you could put in. Precipitation results from oversaturation. Well, how the heck do you do that? Right? Coaches are always saying, give me 110%. Or your parents after a bad test grade. Well, I need you to give it 110%. We all know that's not real, right? You can only do 100%. They mean, of course, is try harder than you've been, do put more effort in, blah, blah, blah. But there, you can't be more than 100% of something. You can be-ish if you stop down. You guys, is The Matrix still a movie you guys watch? Sort of, yeah. I know it's dated, I know. But they had that stop motion sort of thing when that was like the first movie to do that. He'd be dodging bullets and all that awesome stuff. And they go down to that frame-by-frame action. If you think about you making cocoa in that time frame, there is a moment where you could get up to like 101%, and then the solution says, no, we can't do that. And then it goes back to 100. Because here's the thing, we've all made, because of the mugs, okay, we've all made bad hot chocolate. So what do? We put more chocolate in it, right? We stir and stir and stir and stir. No matter what, you still get those clumps. And then when you're done, you get that thing of sludge on the bottom. Here's the weird part, and it's impossible to prove. You just got to trust me on this one. All right? Those aren't the same extra bits of cocoa that were in there when you first stirred it. Those probably dissolved, and another one came out of solution to take its place. They sort of just keep switching back and forth. So that sludge is all extra cocoa, don't get me wrong, but it's not the same one that was left over from when you poured that packet in. Okay? And if they all looked different, you could probably tell, oh, that's Stevie. That was Charlie that was in there earlier, so Stevie's out of solution now. You can't tell, though. Okay? It's constantly going in and out. The water wants, we can't really say that. That's, what do they say, anthropomorphizing the situation. The water doesn't want anything. But it dissolves. That's what it does. All right? And water will, given enough time, dissolve anything, they say. So you get these rocks that water's sitting on. It'll just dissolve them. They go into solution, but only so far. So to achieve this oversaturation, there's a couple ways you can do it. You can either change the amount of water that you have through evaporation in this example, or you could have, and I don't have a better word for this, over-dissolving. You have way too much stuff that could possibly ever be dissolved, and that's a very common situation. So I'm going to throw another chemistry word at you, equilibrium again. You're probably familiar with it. It's not a big scary word. We know what equilibrium means. It's that balance, right? And in this case, that equals saturation. That equilibrium is saturation. So let's say you have actually made the perfect cup of hot cocoa. You actually measured the water. You measured the scoops. You got the right size scooper for starters, right? You measured the water. It is perfect. There's not a flake floating. It's wonderful. But then you forget you're going to your grandma's for Thanksgiving and you don't have any travel mugs and your parents are running you out of the house. So it sits there on the counter as you leave. You come back 4 days later. The water's evaporated out of it. What's in there? All those little floaters or a layer of sludge on the bottom. So you were at a perfect solution, but you threw the water out, and that unbalanced your equilibrium. Okay? Because now that you have less water, you have a lower, I'm going to say by percent composition, by percent value, whatever you want to say. It takes a lot less of Swiss Miss now to stir into that. Okay, so why am I talking about Swiss Miss? Let's actually talk about geology. Let's say you have a giant saltwater lake. I don't know where you'd find one. Maybe Utah. Yeah. All right. Salt Lake in Utah is surrounded by giant deposits of salt called salt flats. You may have heard of them. If you pay attention to car racing and stuff like that, they broke the land speed record out there. Not in a race car, but nonetheless, it was a long, hard, flat area. Visited salt flats a few years back. Pretty cool, pretty desolate, pretty interesting place. They're there because that lake has been shrinking over the centuries. All right, over the millennia almost. And every time more water evaporates out of it, then less water comes in. Well, it hits that, oversaturated in salt, we got to spit some out. And that salt falls out of solution. It leaves a deposit, rings around the bathtub, whatever you want to say. That doesn't just work with rock salt or halite, it actually works with gypsum too. Remember gypsum? Everybody loves gypsum. All right, works with gypsum. A handful of others. Huh?
The drywall stuff.
Yeah. So that's a pretty easy one. You change the amount of water and it throws off your equilibrium. You have to deposit in order to keep that balance. Again, not only does water want to dissolve, water wants to be balanced. So this over-dissolving is a little different. Give me the name of a really popular dancing or bar sort of establishment around here where there maybe you find a line on any given popular night.
Killebrew?
Killebrew. All right, Killebrew has a line out the door? That's surprising.
I don't think so. But
well, that's what I asked for. Come on now.
Packed.
Parking lot's packed. All right. We'll use that if we were talking about, I have another example containing bars. I don't know why. Where we talk about volume and mass. They open their patio, everybody spreads out. That's a density and mass per volume thing. So the rest of you guys, anywhere with a line these days, or we'll make a place up.
Seems more like a gas dispersal type thing.
Okay. Anyhow. Anybody other than him. Okay. All right, so we're going to make a place up. And you've all seen them on TV, right? You got the whole line out front. There's a bouncer at the door, maybe some silly rope, all right? And people are waiting to get in. There's only so many people that could go inside that bar because the health department has codes, and God forbid there's a fire or whatever, you need to supposedly be able to get out everyone in the amount of time and so on and so forth. So you wait there until you and your friends, let's say there's 3 of you, you wait there until 3 people have left. Then you get to go in if you're cool enough, right? All right, so imagine that, but with in water. So you're at this underwater bar now. And the bouncer looks at his watch and says, oh, man, you guys have been here too long. Hold on, just give me a minute. There's these couple that were in a long time. Let me go find them. And he goes and finds someone to throw out of the bar so you guys could come in. Wouldn't that be nice? All right? That's what's going on in this situation. So we talk about limestone coming from seashells. And yes, clams and snails die every day, but sometimes something happens to the water where a whole bunch of them die at once. Okay? If you're familiar with, what's the lake on Sylvan Beach there? Is it Onondaga? No, Onondaga's the one in Syracuse.
It's not just Sylvan Lake, is it?
I don't think so. Oneida Lake, thank you. I knew it had a name. So Oneida Lake every so often gets closed due to algal blooms, okay? That's poison in the water. You're large enough. It doesn't really bother you. It might make you itchy or whatever. But boy, it wreaks havoc on the critters in there, okay? So not a lot of clams or snails, but work with me here. So something happens to the water, similar, and you get a whole bunch of, the entire population maybe even, of clams and snails in the water dies. They fall to the bottom, and they start to decay, okay? So the water's breaking them down, and again, even though we're now on the scenario of a lake, you kind of got to think locally. We're in this area where all these critters are, and sure, the lakes slosh around and so on and so forth, but it's still sort of a contained area. The water doesn't mix that much, at least for my example, because it makes it harder to understand then. But the water can only hold so much dissolved clam or snail. Their shells are made of the same stuff, essentially. They look a little different, but similar stuff. But there's all this dead stuff down there. The water it wants to keep dissolving. So in order to do that, once it hits 100% clam, it starts spitting out calcite, really, so it can dissolve the rest of those clams. That's all that's going on. That's what I mean by over-dissolving. Okay, you've got way more stuff that could possibly be held in solution is sitting there waiting to be dissolved. And that's sort of where I get that bouncer thing, going to get people, pulling them out of the bar so you guys can go back in. Now that's also why when we first introduced the idea of classic, chemical, and organic with the rock cycle, that I told you there might be a little confusion when we get to this point, because I just said we're dissolving clams and snails. And you're like, well, why isn't that organic? Clams are organic, snails are organic. But we're using the word dissolve, we're using the word precipitate. There's no semblance of those clams or snails left here. It's calcite in, calcite out, or snail in, calcite out. All right. So they just don't consider it. And again, I think it's because the dissolving is happening. Now, if you want to take a whole bunch of sticky, semi-dissolved snails and clams, pack them in together, make a nice big old mud ball out of them, set it over there to dry, that'd be organic. Okay. But, sorry for that lovely image this time of the morning. But you dissolve them, put them into water, and bring them back out. It's a magic act. Okay. There's a lot more to it. Again, there's actually one of those 14-week classes I keep talking about. There's an awful lot of topics that get whole semesters devoted to them. But it is true, where you could talk about carbonate geology. All right, carbonate, remember the mineral group carbonates? All right, so it's really all about forming limestone and its cousins. So, of course, it's a little more complicated than I'm telling you in 5 minutes. But that's the gist of it. So, to summarize, because I know it's hard for you guys to sometimes write stuff down when I'm just talking to you. But this is all stuff we just talked about. So, precipitation due to evaporation. A decrease in volume from evaporation causes oversaturation. Right? We said remove the water, throws you out of equilibrium. You have to precipitate to balance again. Gave you an example of Salt Lake in Utah. Salt Lake makes salt. And it's also chock full of sea monkeys. Did you guys know that? You know what sea monkeys are, right? They don't have comic books anymore, but yeah. So it's chock full of them, and it's really actually kind of gross. It has the consistency of like coconut water. But we had to swim in it just, to try and do that floaty thing. They say you're much more buoyant in salt water.
If you want to do that, go down to the Dead Sea.
Not quite as easy to get there, but very true. Very true. I'm not sure they have sea monkeys, though. But they're really cool. I mean, you do get a handful of water, you can see the little guys just spinning around. It's crazy. Precipitation due to over-dissolving. Over-dissolving. And an excess of dissolvable material causes deposition due to oversaturation. See, aren't you glad I turned that into a bouncer example instead of just gave you that definition? Seashells will dissolve into water when the critter dies. There's another slide to follow that thought in a moment here. I know some of you are frantically writing all this down, even though you have access to them online. Watching the pencils. The seashells will dissolve until the water is saturated with calcite. As the water reaches saturation levels, precipitation of calcite begins. So do you still think it's like rain?
To an extent, yeah.
What? How? Whatever.
I'm trying to figure out how to articulate this with terrible with explanations. So the water in the air eventually hits 100%. moisture, 100% humidity.
Mm-hmm.
And eventually, the clouds in the sky will feel that, and oh god, that sounds so stupid.
No, it's okay.
But it makes sense in my head.
I'm sure it does, and it makes sense coming out of your mouth too. You can keep going. But yeah, it's. Back when I used to give short answer questions, I would have people, when I would say explain the process of precipitation, I would have people write about rain. So I have to make a distinction. Yes, it involves saturation of the air. I think, but not necessarily so. Meteorologists might be able to tell me I'm completely wrong. But, we talk more about the phase changes going from gas to water and so on and so forth. And we talk about the little condensation nuclei it needs to get going on there. But yeah, you're definitely off to a good start. It did make sense. So, we all caught up in this slide? So here it is really in a nutshell. Precipitation facilitates continued dissolving. It has to spit something out in order to continue dissolving more. And it just has this innate desire. I keep saying that. Water desires nothing. But it's chemistry. It just is. So to summarize, I'm not a real big fan of that touchy-feely education where they tell you what you're going to need to know, then they tell you all about it, and then in the middle they stop and make sure you know it, and then they tell you more about it, and then in the end they make sure you remember what you were supposed to know. But every so often I try to be that person. So here is a summary slide that tells you what you should have got out of these last two conversations. You need to be able to explain the lithification process for all three types of sedimentary rocks. Arguably name all three types of sedimentary rocks. Presumably that would come up while explaining the lithification process. You need to know some names. We gave you sandstone and shale for clastics. We gave you coal and coquina for organics. We gave you limestone and halite for chemical. And in all cases, I told you there were more rocks. And when you get to this in lab, you'll learn the other examples. When you read the sedimentary rocks chapter, you'll learn more examples. These are just a few. And like I said, I don't have you guys do short answer questions anymore. But like we talked about with the rock cycle, if you could explain it in sentences, you could label any diagram anyone will throw at you. This goes for any class. Okay. So try to be able to explain the process of formation of clastic sedimentary rocks, the compaction and the cementation. And that way, if I ask you some random question about where does the cement come from, you'll be like, okay, the sediments get compacted and then the groundwater flows through, leaving a residue of, the cement comes from groundwater. And you'll be able to go through that in your head. So. Questions, comments, concerns? Yes.
Oh, you are actually looking at me. Okay.
I got peripherals.
How did you spell coquina? Are those both hard C's?
There's a Q. Coquina.
Very Spanish.
See.
Right, thank you.
Yeah. Anybody else? Coquina. Wonderful rock. Wonderful rock. Okay. Excellent.